Any questions, any concerns? Any news on here? Okay, so we're talking about surface integrals. This is going to be the key topic for the last 3 to 4 sessions. So for every surface integral, we should always have a surface integral. Right? We should have a surface. Surface actually is two-dimensional object sitting in the three-dimensional space. Right? So we have a surface. And the most interesting thing, or the most important thing we're concerned about, is so-called the parametric form of the surface. Right? So by parametric form, because it's a two-dimensional surface in R3, so we should have 2 parameters. And we prefer to use u and v, which means we want to use uv to represent x, represent y, and represent z as well. Okay? And u and v as a pair is coming from a region. And if you compare the parametric form of a surface with the parametric form of a line or a curve, in the smooth curve case, we have the parametric equation for a curve, but also we have the orientation of the curve. All right? Remember, we also have the orientation of the curve. In the surface case, it's not so easy to define what the orientation means, but eventually we're going to touch on what it means and how is it going to factor in when we evaluate the surface integral. Okay? So last class we talked about the surface integral of a scalar function. Which we denote the double integral of the function f on the surface. Okay? And the formula says we need to plug in u and v for everything. So I need to replace the function f depending on x, y, z to depending on u and v. Right? So naturally I want to use x, u, v, y, u, v, and z, u, v. But also there is an area element because we're doing this integral on the surface, right? Just like the arc length element when you do the line integral. So the area element is the first product between the 2 tangent vectors. Okay? So this is the tangent vector with respect to the variable u. This is the tangent vector with respect to v. You do the first product, you're getting a area element, and this is actually the length of the normal vector, am I right? This is the length of the normal vector. So if you have a surface, so at any given point, you take the derivative with respect to one variable, you're getting a tangent vector, right? You take the derivative with respect to the other parameter, you're getting a different tangent vector. You do the cross product, you're getting a normal vector, right? This is RU, this is RV prime, and the cross product will give you a normal. Okay? The cross product will give you a normal. However, if we're talking about the orthogonal vector to a given surface, we actually have 2 choices for the normal vector. Right? One is going to the other direction, one is going to the same direction to the first product between these tangent vectors. So when we're talking about the normal vector of the surface, there are actually 2 normal vectors. One is exactly the first product. The other one is the opposite, right? So there are 2 normal vectors. One is given by RU plus RV. The other one is given by minus RU plus RV. Or if you prefer, it's RV prime plus with RU prime, right? And it actually, the orientation of the surface is given by the choice of the normal vector preform. Okay? If you choose the normal vector as always being RU prime cross RV prime, that's going to give one orientation to the surface. However, no matter which normal vector you choose, when we evaluate the surface integral of a scalar function, it doesn't matter. Am I right? It doesn't matter. Because this is given by the length of the numerator. No matter you're taking plus or minus here, it's always a positive number, right? Brian, you got a question? You got a question? Okay, so this is the surface integral we talked about in last week. And I understand this material is going to be much more challenging comparing, especially to taking derivatives. So I highly recommend you to read the textbook afterwards. Okay, there are much more material provided. In class, unfortunately, we have to focus on how to solve questions. But there are a lot of backgrounds of what it means for surface integral, how this area element is coming, and everything. Okay, so in a special case, if f is a constant function 1, taking the surface integral of a constant function 1 on the surface is going to give you the area. Right? So this will give us the area of a surface is equal to S1 ds, which is equal to the double integral along the restriction of u and v, the normal vector. Okay. So I want to give you one example here. So let's say I have a surface z is equal to 2x squared plus y squared. And z is bounded between 0 and 50. I want to find the area. The area of the surface. Okay, let me ask you a seemingly irrelevant question. What does this equation define? It's definitely not a plane anymore, right? We have the square here. So it's one of the quartic surfaces. But which one is it? This is a paraboloid, right? This is a paraboloid. I'm saying it is seemingly irrelevant. In fact, it is actually irrelevant. Because to solve this question, you don't need to know what the type it is, right? But in order to survive in final, you're going to have to know all the 6 different types of quadratic surfaces. This one is a parabola. And if you want to refresh your memory of what it looked like, this one is going to be a paraboloid opening up, right, which is going this direction. It is a paraboloid because if you restrict to the xy trace, if you restrict to the xz trace or yz trace, both of them are parabolas, right? If you make x equals 0, you're getting a parabola. If you make y equals 0, you're getting another parabola. So this is like a rotation of a parabola, okay? Okay, so I want to use this formula to find the area of a surface. So in all the questions involving surface and a line, you're going to have the parametric equations to begin from. This is the key step. You're going to have a parametric equation to begin from. Without a parametric equation, there's nothing you can do, okay? So if the parametric equation is given, then it's wonderful. It is not given, then you should come up with R of u and v, where you have design rules for u and v as 2 new parameters to parameterize both x, y, and z. And for this particular equation, what do you want to assign the rule for u and v here? So the easiest choice is probably I just choose u to be x, v to be y, and z is given by a function of u and v, right? So that would be the easiest choice. So u, v, and 2 u squared plus v squared. But also, I have to come up with what the restriction is for the pair of these 2 new parameters. So by restriction, z is bounded between 0 and 50, which is essentially saying this guy, 2u squared plus v squared, is bounded between 50 and 0. All right? The 0 part is trivial because you have a sum of 2 squares. And the right side is going to give you u squared plus v squared is less than equal to 0.85. So this is the restriction of U and V here. So immediately we have the parametric equations for the surface, but also we have the domain of U and V. Only with these two pieces of information, you can begin evaluating other things. But you gotta have to have the parametric equations here. Up to now, any questions? Any questions about what we're doing here? Any confusion of why we're doing this? So this is the key step. You're gonna have to hammer with the parametric equation. And for this problem, this is actually the easiest case, because you can just assign U and V as X and Y. This is usually our favorite ones. And then if I look at the formula, I need to take an integral of the normal vector, which is the cross product between two tangents. So I have to have the tangent vectors. Okay? So RU prime. What is RU prime? Ellie, work with me. What is RU prime? So this is my equation. I'm simply taking the derivative with respect to U for each component. What do you have?
So it's
1, 0, and 4 U, right? So we're simply taking the derivatives for each component with respect to U. That's what we're doing, right? That's what you got the tangent vector here. So RV prime is going to be equal to 0, 1, and 4 V. And I usually prefer to write it in two consecutive rules. In this way, if I'm computing the cross product, I can simply imagine there's I, J, K's in front of them. And then I'm computing a 3 by 3 matrix, right? So if you want, you can put an I here, J here, and a K here. So the cross product is going to be equal to the I component is 0 minus 4U. So it's going to be minus 4U. So the J component is 0 minus 4V. So it's going to be minus 4V. And the K component is just simply 1. Okay. Now we have the formula over there. We need to compute the double integral of R, the length of this vector, right? The length of this given vector, which is square root of minus 4U squared plus minus 4V squared plus 1 squared d area. So now we're able to reduce the surface integral to a double integral. First of all, these two integrals are two separate things, all right? Do you agree with me? So if I have a double integral, I have x and y, my region is on the xy plane. Whereas the surface integral, you have a function or vector, but this is taking an integral with respect to the surface on its rate. So surface integral and double integral are two separate and different objects, all right? But the whole point of this formula is to reduce the surface integral to a double integral, which we have the full arsenal to deal with. So this is nothing but a double integral with respect to two variables, U and V, where U and V is within a disk, right? This one is actually a disk centered the origin with radius 5. So I'm evaluating a double integral on that region. What do I want to use? A polar rectangle, actually. So this is simply from 0 to 2 pi, from 0 to 5. This one, I got a 16U squared plus 16V squared, which is simply 16R squared plus 1, but I have one extra factor coming here, R dr d theta. Okay, questions? Yeah.
Again, why are we going to polar?
Because this is a region as a disk. Right? So the polar coordinates will be the most first-name coordinates. You can use X symbol or Y symbol, it's up to you. But polar coordinates, if your integrating region is a piece of disk, it's going to be the most easiest one you can use. Okay? And then you can do the following. this is simply a two single variable integration here. So I did my work before the class, so this is going to give me 401 square root of 401 minus 1 divided by 24 multiplied by 1. Okay, again, what I am mostly interested in and what you should be mostly interested in is the step before the evaluation here. Unfortunately, in online homework questions, I keep seeing this. The design is still the questions which you have to compute very large numbers, which you will not see in the final work test. Okay, but every step before the final answer here, you should be completely understanding what is going on here. Okay, so doing a surface integral, I need to begin from a parametric equation, okay, which I need to design what rows I want to assign for u and v, and then I need to come up with the tangent vectors on the u direction and the v direction, and every surface integral involves the normal, which I need to do a cross product between these two vectors. And when you compute the area, it's simply the integration with respect to the length of the normal. Okay? Questions? Okay, now I want to go to introduce the surface integral of vector field. Because we are now on a surface in R3, so our vector field is also a vector field in R3. So I have a x component, y component, and z component. Okay, so this is the vector field in R3. So the surface integral of a vector field on a surface S is going to be written as S f dot n ds. Okay. So still, I want to refresh our memory about the line integral of vector field we did before. If we have a surface, if we have a curve, and we have a vector field, we can actually compute two things: the circulation and flux, which is the integral of the vector field dot product with the tangent and the dot product between the vector field and the normal. All right. So if your intervening region is a curve, you can actually do two line integrals of a given vector field. One is the dot product between the vector field and the tangent. That's going to give you the circulation. If you do the dot product between the vector field and the normal, you're going to get the